All right, so this is the topic, minimum cost network flow problems. And basically what I'm going to do is I'm going to give you the description of the definition of the problem. We'll talk about some properties of this as a linear programming problem. It's a special class of linear programming problems, and because of the special structure of the network flow problems, you can use more efficient algorithms to solve the problem. We're going to see a specialized version of the simplex algorithm as specialized to the network structure. However, there are other algorithms that have nothing to, or that have little to do with network simplex. So, first of all, of course, we need to define graphs and networks. A graph, G, is a set of two sets script N, script A. I'm going to use regular A, capital A, for something else, so I'm just using scripts just for that reason. A graph is a set of two sets where the first set is just a set of finitely many objects, whatever they are. Okay? So let's assume we have m objects. You can use the integers 1 through m, or you can use however you wish to refer to the objects. For example, cities of Turkey, 81 cities, Ankara, Adana, etc., whatever. Zonguldak is the last one, so if you just list them, they are the nodes of your network. And A is just a subset of cross product of the first set by itself. Okay? All right. So the first set is called the set of nodes here. Each element of script n is a node. Some people refer to them as vertices. Not the vertex of a polyhedral set, but just as a vertex. And A, the elements of that are called arcs. We are talking about directed arcs here, because I'm taking the cross product of n by itself. So each element of A is a pair of elements ij ordered. Okay? So ji is different from ij. All right, so as an example, this could be a graph. In this case, let's also have two more nodes here, 5 and 6. This graph has nodes 1 through 6. Okay? And the arc set consists of 1, 2, 2, 3, or 2, 2, 3, 2, 4. What else? 4, 2, 4, 1, 4, 2. And 5, 6. And 6, 5. So the set of two sets, N and A, where A is a subset of the cross product of the first set by itself, defines a graph. The graph may look disconnected, as you see in the picture. This is just a drawing, so drawings are not good enough. You need the algebraic, or you need to list the set of elements of each set to be precise. Let me give you additional definitions here. By the way, usually if you associate certain numbers with nodes or arcs or both of both nodes and arcs of a graph, then you have a network. These numbers are used for modeling purposes. For example, the numbers you may assign to arcs may be positive numbers, which may represent the time to traverse that particular arc, or it may be the potential difference between the end nodes of the arc, or whatever. It may be a cost associated with the arc, or you may have numbers associated with nodes, which may represent, for example, the demand that's being pulled at that particular node, or you may have sometimes supplies available at the node, so on and so forth. So it depends on what you want to do. And such structures, of course, graphs are very general. And there are also the hypergraphs, which I'm not going to go into. Okay, so let me just continue with some definitions here. Let's define the concept of a chain, for example. A chain is just a sequence of nodes and arcs, which may, for example, as an example, I may have node 1, and then arc 1, 2, and then node 2, and then arc 3, 2, and then 3. That would be a chain which begins at node 1, and then the next node is 2. There's an arc 1, 2 here. I'm looking at this example. Okay? And then you have node 3. You've got this. So this is a chain. So in the formal definition, you have a sequence of nodes and arcs such that every arc in the sequence has end nodes defined by the immediate predecessor and immediate successor nodes. Okay? That's the definition. A path is similar to a chain, except that in this case, all the arcs are in the same direction. For example, here, this is not a path, whereas if you have 1 to 2 and then going 2 to 4, this would be a path. So in this case, the arcs listed in the chain, they all are oriented in the same way, meaning that every, well, you know, in this case, it will be 1, 1, 2, 2, 2, 4. So every arc listed in the path begins at the preceding node and ends at the successor node. Okay? Succeeding node. Okay. And then we have cycles and circuits. A cycle is just a chain which comes back to itself. So, for example, a cycle here would be 1, 1, 2, then 2, 2, 4, then 4, then 4, 1, and then 1. So a cycle is just a chain with the beginning node and the ending node the same. Okay? That's the cycle defined in this way. That's the cycle we're talking about here. Okay? Did I do it right? 1, 2, 2, 2, 4. Oh, 2, 4 or 4, 2? I meant to have 4, 2 here. Why don't you change it to 4, 2? Yeah. Let's just change it to 4, 2. So it will be different from a circuit. Okay? A circuit is similar to a path. So you begin and end at the same node. That's your path. All the arcs are in the same orientation in a path. Okay. We say a graph is connected or weakly connected. So let's separate weakly and strongly connected. So we say a graph G is weakly connected if there is a chain between any pair of nodes of the graph. Okay? You can get from any node to any node. In the example problem, in the example graph, this is not connected. Why is it not connected? Because, for example, between node 1 and 5, you don't have any change. Okay? Strongly connected if there exists a path from any node I to any node J of the graph. Okay? All right, so here's a simple example. This graph is weakly connected, but not strongly. Why? Because, for example, or is it also strongly connected? Actually, yes. I have a path from 1 to 2, then to 3. Yeah, it's also strongly. Yes, sorry. It's also strongly connected. A component refers to a maximally connected subgraph of the graph. So I need to define subgraphs first. Let's talk about subgraphs first. See, to be able to define something, you are not supposed to use any term that's not already defined. Okay? Always remember that. All right, what's a subgraph? A subgraph of a graph G is another graph where the node set is a subset of the given graph. Of course, we're talking about a subgraph of a graph G. Okay? So the node set is a subset of the original subgraph of G. And A prime is a subset of A with the additional property that says that whenever an arc ij is in A prime, then I and j are both in M prime. Okay? A spanning subgraph is just a subgraph, a spanning subgraph of G again. A spanning subgraph of a graph G and A is a subgraph G prime with the additional property that M prime is actually equal to N. So it contains all the nodes of the graph. Okay? That's a spanning subgraph. So a component of a graph G is a maximally connected subgraph of G. So let's suppose this is the graph having all these arcs and the nodes 1 through 5. In this case, I may look at a subgraph where M prime contains, for example, nodes 1 and 2, okay? And A prime contains arc 1, 2. Suppose that's the subgraph under consideration. So this subgraph has, if you just draw it here, has 1, 2, and the arc like that. So this is the subgraph I'm talking about. Now, is this a component? The answer is no. It's a subgraph, okay, but it's not a component. Why? Because it's not maximally connected. Okay? There's a larger graph here, or a larger subgraph here, consisting of nodes 1, 2, 3, and the arcs, all of these that you see here. That's a maximally connected subgraph, whereas this one is not. So for a component, this would be a component. This is another component. These are two components of the graph under consideration, because this one is connected and it's maximal with respect to the property of being connected. Okay? Maximal in the sense that it includes all possible nodes that are connected to each other. This one is also. Okay? Now, here's an important concept, tree, a special type of graph, which we're going to use quite often in the context of network flows. What's a tree? A tree is a tree on M nodes is a connected graph with no cycles. Okay? That's what a tree is. So here's a tree as an example. This is a tree. On 6 nodes, you can see that it's connected. You can get anywhere. Well, when I say connected, I mean weakly connected. Okay. Whenever I use the term connected, I mean weakly, unless otherwise specified. All right. So this is weakly connected or connected, and it has no cycles, and so it's a tree. This is also a tree. That's where the terminology comes from. You know, things that look like trees, they are called trees. Graph terminology has a lot of this stuff. They also use forests. So if you have a graph whose components are trees, then you have a forest. Okay? So let's also give that definition. A forest is a graph whose components are trees. Okay. All right. What else do we have? A spanning tree. A spanning tree of a graph G is a subgraph C of G where n prime is actually equal to n. So it's spanning subgraph, and T is a tree. So any subgraph that is a spanning subgraph, which also has the property of being a tree, is a spanning tree. Okay? That example that has two components has no spanning tree. Why? Because it's disconnected. Okay? A spanning tree must be connected by definition and must contain all of the nodes of the original graph. But this, for example, has a tree. For example, if you just pick these ones, that would be a tree, spanning tree. If you just delete this arc, you'd get a spanning tree of the graph. Okay? I think that's pretty much enough for definition, so let's get to the business now. So, with that terminology, we can define the minimum cost network flow problems in the following way. We have a graph G with node set N, arc set A, and I'm going to assume that I've got, say, M nodes and N arcs listed in some way. I'm going to assume that the nodes are numbered from 1 to m. With the following data. So we're talking about a network now. You have a number bi, which is the so-called requirement at node I. This is given for each I in the node set. And if bi is a positive number, then node I is a supply node. If bi is a negative number, then node I is a demand node. So it wishes to receive some number of units of a given product, for example. This is in the context of distribution problems, for example. If bi is 0 for node I, then it's a chance shipment node. So we're essentially talking about, for example, the highway network or the road network of, say, Turkey, okay, where the nodes are, say, cities as well as smaller, what do you call them, whatever, the administrative units. And then the arcs are simply the road segments. If you, for example, if you are the Tofaş factory in Bursa, you are sending, say, spare parts to different cities in Turkey using the highway network. In that case, you have a supply of all those units at Bursa. So bi would be positive, maybe say 1,000 units for I equals Bursa. Okay? And if you have demands at Kayseri and Ankara and Izmir, as well as many other cities, then they will each require some parts on a weekly basis. There's always a unit time under consideration. Let's, for example, assume the unit time is 1 week. So on a weekly basis, you just require these truckloads of shipments, and that's what your demands will be. Okay? And whenever BI is 0, you can visit that node along the way when you distribute these, or when you get these units from sources to sinks, or from supply nodes to demand nodes. So these are called also sources. Demand nodes are also called sinks. When you deliver units, truckloads from sources to sinks, you may along the way visit certain nodes which neither supply anything nor demand anything. They are transshipment nodes, so you are allowed to visit them. Okay? All right, we have additional data. We have a data Cij, cost of 1 unit of flow in arc Ij. This is given only for defined arcs. Okay. What else do we have? You may also have upper bounds. You may also have lower bounds, but for now, I'm going to, for the time being, I'm going to omit the lower bounds, okay? For the more general case, you may also have lower bounds. Upper bounds are also omitted also. So let me just write down Lij for the lower bound on flow in arc Ij. Again, only for arcs that are defined. Assume for now that Lij's are 0 for all arcs, and upper bounds are infinity. In other words, there's no upper bound for every arc, okay, just for the time being. So in this case, under these assumptions, the network flow, minimum cost network flow problem is referred to as actually a transshipment problem. You might want to take a note of that. Okay. All right, so that's the data. What is required is the following. Send units from sources to sinks via arcs of the network so that the total flow is conserved at each node and the total cost is minimized. That's the basic requirement. What do I mean by flow is conserved? What that means is, if you look at any node, say I, whatever comes in as a flow will go out also. So the total inflow equals total outflow. That's what it means. Flow is conserved. Okay? All right, here's an example. Well, actually, before the example, let me give you the general formulation. So let's define Xij to be the flow in arc ij. These are the amounts to be determined. They are your unknowns. Okay? So the formulation for the problem is the following. You are minimizing the total cost defined by the unit cost in arc ij times the total flow in arc ij. Of course, when I say flow in arc ij, it goes from I to j. Okay? So it's directed. This is summed over all possible arcs. Subject to. We need a flow conservation equation for each node. So I'm going to write it down for node I. What goes out at node I, if you look at node I, there are many outgoing flows here. For example, J, K, L, etc. This will be Xij, the amount going here. Okay? Which could be 0, but could be also positive. Anyway, you've got other flows. So you're summing over all j such that ij is a defined arc. This is kind of too small. Let me just write it a little bit larger for the camera. This is for fixed I. You sum over all j such that there's an arc from I to j. Okay? Minus the total inflow at node I. So this time you have, again, summation over j. This time you're looking at these ones. And you're summing over all those nodes j, the flows coming from j, where ji is a defined arc. Now this will be equal to bi. And this is written down for each I. Now if bi, let me have your attention here. bi is a given number. If bi is 0, this is a transshipment node. So all that comes out, the first part here, that's the outflow, is equal to the total that comes in because bi is 0. Okay? If bi is a positive number, that means there's a supply at node I. So in that case, there's a supply of bi units coming into node I as an external inflow. You are supplying so many units. Of course, that's an inflow at node I, which would be a negative number here. For example, if bi happens to be, say, 10, that would be included in this part as minus 10, because it's an inflow, which becomes a plus 10 here on the right side. Okay? So that's why your positive bi's are supplies or inflows. If bi is a negative number, in that case, bi will be, for example, minus, say, 5, in which case that means you have an external outflow of 5 units. Not minus 5, but 5 units. Okay? So that outflow would be a plus 5 on the left side, but it becomes a minus 5 on the right side. So these things make sense. That's all I'm trying to explain to you. All right. This is not finished yet. We also have xij's greater than or equal to 0 for every arc ij. For the case, lower bounds are 0, upper bounds are infinity. Okay? In the more general case, we're going to have xij's also bounded above and below. But for now, let's just deal with this situation. Okay, this is the minimum cost network flow problem with this non-negativity, and it's called the transshipment problem. As a special case of the minimum cost network flow problem. Okay? Please open one more window. It's too warm here. He's busy with the camera. Okay, in this example, if you look at the sum of the BIs going from 1 to 4, they add up to 0. This is the balanced version of the problem. In other words, the total supply made available to the network at the sources is equal to the total demand required at the sinks. In this example, we have externally 4 units being supplied at node 1, and we have externally 2 units being made available at node 2. And then node 3 has a demand of 1, so it pulls 1 unit out of the network. And this one has, number 4 has 5 units pulling out of the network. So we have a balanced problem. We have the variables xij's, for example, x12 along this arc, so on and so forth. And if you wanted to write this down as a minimum cost network flow problem, I'm assuming Lij's are 0, Uij's are infinity. In this case, you've got 2 times x12 plus minus 5 times x13 plus minus 1 times x23 plus 4 times x24 plus 6 times x32 plus 3 times x34 plus 7 times x41. That's the objective function. Subject to, for node 1, I have an outflow of x12 plus x13, and I have an inflow of x41. Inflows are negative. The requirement at node 1 is 4, so they should give you 4. The balance is 4. Okay? For node number 2, what do we have? We have outflow of x2, 3. We also have x2, 4. We have inflow of x12. And then what else? We have inflow of x32. And then the total is equal to 2. Node number 3. Outflow 32. And then 3/4. Inflow of 1/3. And then inflow of 2/3. That's equal to -1. Node number 4, outflow of x41, inflow of x24 and x34 is equal to -5. And then you have xij's greater than or equal 0 for the defined arcs. Okay? All right, we simply wrote down a flow balance equation for each node. That's it. And nothing is created at the nodes. Nothing is destroyed. However, all right, so you may have externally supplied or required amounts at the nodes. This is the flow formulation. If you look at the matrix of coefficients here, that's called the node arc incidence matrix. So I'm defining a matrix A here whose rows correspond to the nodes and whose columns correspond to the arcs. So the first one is associated with the variable x12, x13, etc. Okay? And that's simply the left-hand side, the matrix of left-hand side coefficients here. You can see that the first column has a 1 here, -1 here, zeros in nodes for nodes 3 and 4. 1, 3 has a +1 here, -1 here, zeros elsewhere. 2, 3 has +1, -1 with zeros elsewhere. And what else? 2, 4 has 1 and -1, like that. 3, 2 has 1, -1, 0, 0. 3, 4 has 1, -1, 0, 0. 4, 1 has +1, -1, 0, 0. It's got this structure. Every column has exactly, or has, a +1 and a -1 and zeros. 1 +1, 1 -1, and zeros. That's an important special property of this matrix. This is called the node arc incidence matrix. And from now on, we will be using that particular matrix to refer to minimum cost network flow problems in compact form. We'll just use this form. Where A refers to the node arc incidence matrix, C is just the vector of cost, X is the vector of Xij's, B is the vector of requirements, Bi's. Okay? So C is Cij, it's n by what? 1, right? You've got n arcs, so it's an n vector. A is m by n, m rows corresponding to nodes, n columns corresponding to arcs. And B is, that's m by 1. And X is the vector of Xij's, where Ij is the Ij arc. It's an n by 1 vector. And that would be the, okay, so here A is the node arc incidence matrix of the network. Next time I'm going to give a formal definition of A, and then we'll carry on after that, okay, based on that information. So take a 5-minute break. I'll give you your exam papers, and then maybe I'll go over some of the questions that might have given you particular difficulty, and then you'll have an example on decomposition from Hatice. Actually from me, but she will present it, okay? Peki.